All right, so today we are going to do 4 free response questions on rates. All right, so the first one, take a look. You're going to be doing some Riemann sums in these. We'll do right, left, trapezoidal, midpoint. I tried to get a couple of all of these, and then these are the ways that they could ask these types of questions. All right, so Joanna jogs along a straight path from time equals 0 to 40. Her velocity is given by a differential function v, so there's a derivative, meters per minute. So think of that, this is position, this is time. So you've got position, then you've got velocity, then you have acceleration. So we've got to think about those things. Remember, we had our position, I'll put it over here, our velocity, and our acceleration. This was going to be in some sort of distance, like meters. This would be in some sort of distance per time. So in this case, we're meters per minute. And then acceleration would be meters per minute squared. Okay? Also remember, if you're going down, you're doing the derivative. If you're going up, you're doing the integral. So those are just some things we need to remember as we're going through these. All right, so number 1 says, use the data to determine to estimate the value of v prime of 16. All right, well, first of all, we're going to think about what v prime of 16 actually is. So v prime is going to be the derivative, okay? The derivative is the slope of the tangent line. Now, they want you to estimate it. Well, if you're looking up here, you don't have 16. You've got 0, 12, 20, 24, 40. So 16 is going to be somewhere in between 12 and 20. So you're going to estimate, you're going to use the slope of the secant line to estimate the slope of the tangent line at 16. Now, you're using the points v at 12 and v at 20. So, in order to get the slope of the secant line between 12 and 20, we're doing y minus y over x minus x. So 240 minus 200 over 20 minus 12. I've already done the math, so that's 40 over 8, which gives you 5 meters per minute squared. You've just found the acceleration. Now, I don't ask you for that, but you need to be aware of what it is that you're finding and how you're finding it. So we estimated the slope of the tangent line. You can only use the information that they give you. So you're going to go somewhere in between in order to find it. All right, let's look at part B. Part B says, using the correct units, explain the meaning of the definite integral from 0 to 40, the absolute value of v of t. Now remember, when we were talking about displacement versus total distance. Displacement, well, when we started at Amani, and we walked all the way to Thomas, and then we turned around and we came all the way back to Amani, and we didn't go anywhere. Our displacement was 0, but our distance, our total distance, was a lot. Why didn't I walk to Robert? I don't know. Anyway, you're walking all the way over there, you're coming back. Well, we did walk the length, or I walked the length of the classroom. So that's total distance. So that was absolute value. It didn't matter that I turned around and came back. So absolute value means everything that's negative becomes positive, and it's your total distance. So it says using correct units. So you want to make sure that you're putting the units in there as well. So you're going to say the total distance when Joanna travels or jogs. And then, what did she do? She jogged in what? In meters. And when did she do it? From t equals 0 to t equals 40. How do you know 0 to 40? Well, you're looking at this integration from 0 to 40. Okay? Oh, and I didn't walk all the way from Amani. I walked all the way from Jordan, didn't I? Because Jordan was in the front. So if I went from Amani, I'd have to kind of like turn a corner. Anyway, oh, our classroom. All right, so getting back to our problem here. So it is the total distance Joanna jogs in meters from 0 to 40. You want to make sure that you're getting in, that it's the total distance, that she's jogging in meters, and then the amount of time that you've got going on. Okay? All right, now the second part of this problem says approximate the value of 0 to 40 absolute value using a right Riemann sum with 4 subintervals indicated in the table. Now, you do get your calculator. So you're saying, oh, well, why can't I just put this in my calculator, the absolute value? You could, but you're not doing what it is that they want you to do. So this is how they're going to get around, you know, I can use my calculator versus I cannot. They want to see a right Riemann sum, and they're going to need to see all the little pieces that go with it. All right, so let's break this up. Excuse me, we're going into 4 subintervals. So 0 to 12, 12 to 20, 20 to 24, and 24 to 40. Okay? So we want right. That's right, 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 right. We need to know our change of x. What's our distance with all of these? Well, between 0 and 12 is going to be 12. Between 12 and 20 is 8. Between 20 and 24 is 4. And between 24 and 40 is 16. Now, I'm not using the 12. I'm using the y value of 12. So looking here, let's see if I can get both of these in here at the same time. Looking here, the y value of 12 is 200. So I'm going to do the change of x, which is 12, times the y value of the 12, which is 200. Plus the change of x, which is 8, times the y value of 20, which is 240. Plus the change of x times the y value of 24. Now, look at that. That's a negative 220. Okay, now we're doing the absolute value, so we have to be super careful, and we need to make that a positive 220. Now, if you accidentally make that a negative 220, you're still going to get some points. You're not going to get all the points because your answer will be wrong, but you are still going to get some points. So just remember to make that positive. Just pay attention to the little details like absolute value. All right, then we have plus 16 times the y value of 40, which is 150. Now again, I've already done the math, I've already added that up, and it's 7,600, and that's going to be meters. Now, why meters? Well, we've gone from meters per minute, we've integrated, which means we got rid of the time, and we're up here at meters. All right, part C. That was part B. Part 2. All right, now we're on part C. Part C says, Bob is riding his bicycle along the same path from 0 to 10. Bob's velocity is modeled by this, where t is measured in minutes. B of t, is measured in meters per minute. Find Bob's acceleration at time t equals 5. All right. All right, so they gave us Bob's velocity. They want Bob's acceleration. All right, so b of t is equal to t cubed minus 6t squared plus 300. And they want us to find his acceleration. Well, if this is velocity, acceleration, we're going to get by doing the derivative. 3t squared minus 12t. I wrote the right thing, said the wrong one. We want to find that at 5. And I already put that in my calculator, and I ended up with 15 meters per minute squared. Now again, they didn't ask for units, but we're just going to practice our units, just in case they ask. Okay? Any questions on part C? Ah, good. Can't ask anyway. You can through an email, just not on my video right now. All right, part D. Based on the model B from part C, find Bob's average velocity during the interval 0 to 10. Now, we just learned average velocity a short while ago. A to B of we're doing average velocity, so it's v of t dt. All right, so we're going from what, 0 to 10? So that's 1 over 10 minus 0, the integration from 0 to 10 of that b of t that they gave us. Now, again, you're going to have a calculator. So you can use your calculator. Just be careful, guys. When you submit your test, they're not going to know what it is that you've got in your calculator. So make sure that you're writing this down before you put it in your calculator. And we're going to do 1 over 10 times math 9 from 0 to 10 of our function. And our function was what? T cubed minus 6t squared plus 300. That was his velocity. And you go ahead and you get the answer of 350. Now, this is average velocity, which means you're still in the velocity unit, so you're still meters per minute. All right, so that finishes off number 3. Let's go ahead and look at number 1. All right, now number 1 is going to give you these ugly rates right here. So the rate at which rainwater flows into a drain pipe is modeled by this right here. And it's measured in hours. T is measured in hours. Cubic feet per hour. That's the rate of volume, cubic feet, from 0 to 8. The pipe is partially blocked, allowing water to drain out the other end. And here's the drain, cubic feet. So it's leaving the drain by this formula. There are 30 cubic feet of water in the pipe at time t equals 0. We need to make sure that you underline that or you write that down again. You're going to need that at some point. They wouldn't have given it to you if you didn't need it. Okay? How many cubic feet of rainfall flows into the pipe during an 8-hour time period? All right. Now here's my advice. When they give you ugly equations, you don't want to type those a million times. My advice to you is to go ahead and put them in your calculator one time. So you got 20 sine of x squared over 35. That's the first one. Your second one, you've got negative 0.04 t cubed plus 0.4 t squared plus 0.96 t, or x. Now, what I would want you to do at this point is just to really double check to make sure you typed it in right. You would hate for all of your things to be wrong because you typed it in wrong. Now, that's another reason why we're typing it in y1 and y2. We only want to type it once. We're going to then use y1 and y2 in our calculator rather than having to type it all over again. Now, if you forget to use this, it's fine. You can type it in each time. It's just, this is a time saver. Okay? All right, so it's in. So now it says how many cubic feet of rainwater. So this formula is cubic feet per hour. Well, I want to get rid of a time. When I'm getting rid of a time, I want to integrate. So I'm going to integrate from 0 to 8 of that r. I'm going to integrate from 0 to 8 of that r of t. Now, I'm only doing the r of t because they only wanted to know the rainwater flowing in. Well, so we're going to math 9 this thing from 0 to 8. Now, I would have to type in that r of t sine thing, which you could do, sure, but you've already typed it in. So now you can use that alpha, ooh, is it graph? No, it is not. Was it alpha trace? Aha, it was. It was alpha trace, although I'm not in the right spot, am I? Get into my little spot right here, and alpha trace, and I want to do the y1. And you go ahead and you enter, and you get 76.570. Now, that is just going to be in cubic feet. Okay? All right, so moving along. Let me move this up here. Is the amount of water in the pipe increasing or decreasing at time t equals 3? Give your reason for your answer. Well, think about it. You've got the rate of the water coming in, and then you're subtracting the rate of the water coming out. And you want to know what's happening at time t equals 3. So you want to look at r of 3 minus d of 3. All right, well, how can we use what we've got in our calculator to do that? Well, the store button is the easiest thing. You've got x being 3. I did 3, and then I hit STO right here, and then I hit x. So 3, then the STO, then the x, and then the enter. Now, every time I hit x in the calculator, it's going to say 3. Now, if I wanted to recall y1, so just do alpha trace, and I want to do y1, then it's going to plug in the 3. Now, I wanted to do y1 minus the y2. So I'm going to highlight that y2 and put that in there. So y1 minus y2 when x is equal to 3 is a negative 3.14. 0.314. Now, since that's negative, the water is decreasing at times t equals 3. So when the time was equal to 3, the water was decreasing. All right, let's take a look at part C. Part C says, at what time between 0 and 8 is the amount of water in the pipe at a minimum? Now that means absolute minimum. Now when we're talking about absolute minimum, you need to make sure that you check at the endpoints. So at t equals 0 and t equals 8, and the critical points. Now, remember, how do I find the critical points? I set the derivative equal to 0, right? Now, they gave you the rate, which means they gave you the derivative. So you're looking pretty much at what we looked at up here at B. You want to find when the rate minus it leaving, so in versus out, is equal to 0, because that is going to be where you find your critical points. Okay? Now, how could we do that on our graphing calculator? I'm going to show you graphing calculator, and I'm going to show you again. Sorry, my light up above is kind of reflecting in here. So I'm going to show you how I'm going to do it in the graphing calculator. I'm going to show you Desmos, which is a little bit easier. So here, I want to put in y1 minus y2. Now, I don't want to look at these two graphs. Oh, don't hit clear. Because I don't want to have them mess up my graph here. Now, I'm only looking between time of 0 and 8. So I'm looking at this graph right here, and I'm going to need to find out where it crosses the x-axis, somewhere between 0 and 8. Aha, it just did it, right here. Right? Notice how slow this thing is moving. So I want to find out where it crosses that x-axis. So I have to do second calc, and I want to calculate the 0, which is number 2. And it looks like it's going to be between 2 and 4. So left bound is 2, right bound is 4. Hit enter. And I find out that it's at 3.272. Okay? Now, that wasn't so bad, right? Let's take a look at Desmos. I should have just left it in Desmos, but I didn't. All right, so here's my Desmos. Now, for Desmos, I'm going to have to type the whole thing in. So I've got 20. Let me show you what I'm typing. I have 20, and then I got to find sign, so I go over to functions, and there's my sign. And it's x squared divided by a 35. Okay? Then I want to subtract the water coming out. So I've got a parentheses of a negative 0.04 t cubed. Now, cubed, I'm going to do my back arrow here and make that a 3. All right, so then we've got plus 0.4 t squared plus 0.96 t. All right, so I typed it in, and so here's my graph right here. Okay, I want to find out where it's crossing the x-axis. I hit that button right there, and I got 3.272. So, I don't know, this one, I had to type it in yet again, but that just didn't take very long. Clicking a button with my finger is way easier than doing the left and the right thing. So, Desmos might help you a little bit, so just keep Desmos in mind, okay? All right. So anyway, we got 3.272. So we need to figure out t of 0, t at 3.272, and t at 8. Okay? T at 0, t at 372, and t at 8. Now where are we plugging this in? We're going to plug this into some sort of an equation. So let's talk about what equation we have to have. Now, this, what was it, like a drain pipe, started with 30 cubic feet of water in it. Okay? Then, the amount of water was going to be found by, from 0 to whatever time it is, and really, I think these are going to be x's, because if we're thinking about the second fundamental theorem of calculus, these were x's. And remember, the time went in there. All right, so you've got 30 plus the integration from 0 to t of r of x minus d of x dx. Now, if you were to write r of t, d of t, dt, they're probably not going to take off for it. They just want to know how much value is in all of these. Now think about it. When time equals 0, you knew that there was 30 cubic feet in there because the integration from 0 to 0 is going to be nothing. So you don't have to put that in your calculator. Now, for this next one, you can just put that in your calculator as you see it here. We've got 30 plus math 9. We're going from 0 to t, which would be 3.272 of r of t. So we've got alpha trace y1 minus alpha trace y2. Another reason why we put those in y1 and y2. Helps us so much, makes this go so much faster. You don't have to type those equations in all the time. And you end up with 27.965 cubic feet of water. Now, doing 8, all you're going to do is you're going to redo this whole thing just like this. Only instead of this 272, or 3.272, you want an 8. So you hit enter, and you're going to end up with 48.544. So right there is where you have the least amount of water. Okay? Least amount of water at t is equal to 3.272. All right, so now we're looking at part D. Part D says the pipe can hold 50 cubic feet of water before overflowing for time greater than or equal to 8. Water continues to flow into and out of the pipe at a given rate until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. The time W. All right, so essentially all we're doing is this equation. Only we're going to put a W right here. We're going to put T's in here, and we want to set it equal to 50. So we started with 30 cubic feet of water, okay? You want to add the integration from 0 to what time of r of t minus d of t dt. And you want to know when it'll equal 50. Because as soon as it equals 50, that's when it's going to start to overflow. Now, could you set this equal to 20? And the answer is yes, you could, because you know that it already has 30 in it. So when, with the filling and the draining, is this going to equal 20? Because once it equals 20, the 20 plus the 30 equals the 50. So that's another way you could have set it up as well. And yes, they would have accepted it. Now, because they specifically said your time is equal to W, you want to make sure your W is right there. Now, if you made these X's, would that be completely wrong? I don't think so. I don't think that they would take off for that. So if you had from 0 to W and you had R of X minus D of X dx, I think you'd be okay. Although I think probably you would have T's instead of X's anyway. All right, so that's number 1 and number 2, or number 3 and number 1. Let's go ahead on to the next page. I'll stick here. This piece of paper. All right, so hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup times 0 to 6 is given by the differential function C, where T is measured in minutes. Select the values of C of T measured in ounces are given in the table above. Use the data to approximate C prime of 3.5. Well, we just did this in the very first one. So you're doing the exact same thing that you did before. You're just finding the slope. In between, so you want 3.5, so you're trying to find it between 3 and 4. So for part A, you're going to do 12.8 minus your 11.2 over 4 minus 3, and I already did the math for this. You get ounces per minute. Okay? Now, it did want to indicate units of measure. Well, these were the ounces up here. That was the time. So ounces per minute is right there. And you're done. All right, part B. Is there a time, t, between 2 and 4 at which C prime of t is equal to 2? Justify your answer. Now, this is going to kind of be the mean value theorem. So basically what you need to do is show the mean value theorem, because mean value theorem is going to make the slope of the secant equal to the slope of the tangent. Okay? And you want the slope of the tangent to equal 2. Right? So you have to look at the slope of the secant line. So the slope of the secant line between 4 and 2 is 12.8 minus 8.8 over 4 minus 2. Aha, which is equal to 2. That's the slope of the secant. Which means, because this thing is continuous and it's differentiable, okay, between 0 and 6, it's continuous, there aren't any holes, they didn't tell us any, it's differentiable everywhere along there. Because it's differentiable and continuous, by the mean value theorem, there is a point between t equals 2 and 4 where C prime of t is equal to 2. Now, as long as you show them that you know that the slope of the secant line is 2, and you say MVT, you don't even have to say mean value theorem, because they know what MVT is. Now, you could write it all out, mean value theorem, and that would be just fine. Okay? All right, let's look at part C. Part C, use the midpoint sum with 3 subintervals of equal length indicated by the data to approximate the value of 1/6 of 0 to 6 of C of t dt. Use correct units, explain the meaning of what it is that you have found. Okay, so 3 intervals. So if we're doing 3 intervals, we're going to go from 1 to 2, 2 to 4, 4 to 6. Sorry, 0 to 2, 2 to 4, 4 to 6. There's our 3 subintervals. Midpoint. Your middle is 1, 3, and 5. Your change of x is equal to 2. From 1 to 3 to 3 to 5, your distance is 2. So, midpoint formula. You want to always multiply by 2 And you want the y value of the 1, which is 5.3, plus 2 times the y value of the 3, which is 11.2, plus 2 times the y value of 5, which is 13.8. Okay? Now, 1, 3, and 5, those aren't the distances, those are the midpoints. Okay? 1 is the midpoint between 0 and 2. 3 is the midpoint between 2 and 4. 5 is the midpoint between 4 and 6. You want to use those y values for your height of your rectangle. You're multiplying by 2 because that's the width of your rectangle. Now, I already put this in my calculator, and I got 60.6. Don't forget to multiply that by 1/6, because they want 1/6 of it, which is 10.1. Now, they want your units, and they also want to know what it is that you just found. Well, if you're doing 1/6 of the integration, we just did that a little bit before. That's called average value. So you found the average value of the water in ounces from t equals 0 to t equals 6. The average value of water in ounces. Now, why ounces? Well, because take a look at what they've given you. They've given you ounces. You're finding the average amount between 0 and 6. Okay? 10.1. All right, part D. Part D says the amount of coffee in a cup in ounces is modeled by this ugly equation. Using this model, find the rate at which the amount of coffee in the cup is changing when t equals 5. So, modeled by this, b of t. And they want you to find the rate at which it is changing. All right, so they gave you in ounces. You want to find a rate, which says to me derivative. So you want to find b prime of 5. Okay? Now, b prime of 5. Now, if you weren't given a calculator, you would have to go ahead and you would have to do the derivative. But remember, this is weird times, and you get to use your calculator. So please do not do the derivative by hand. I know that you can, but it's just going to take you time to do so. What if you forget the chain rule or something like that? What if you forget the negative? Use your calculator. Math 8 is going to be our derivative. Remember Math 8? d dx of our function. Make sure you're typing it in right. So we have to type it in right. 16 minus 16e to the negative 0.4t or x. And we want to evaluate it at 5. And we get 0.866. We're done. 0.866. And that is going to be ounces per minute. Okay. All right. So let's look at the next one. The last one, number 2. I had some trouble with this last one, mainly because I just didn't read. So, you know, reading is good. Number 2. Concert tickets went on sale at noon, t equals 0, and were sold out within 9 hours. The number of people waiting in line to purchase tickets at the time t is modeled by a twice differentiable function. L for 0 to 9. Values of L at various times are shown in the table above. Use the data in the table to estimate the rate at which the number of people waiting in line was changing at 5:30, so t equals 5.5. Show the computations to lead your answer, indicate in units of measure. This is now the 3rd time we've done this one, so this is a popular question. You want to find and you want to estimate the slope between 4 and 7. Why? Because 5:30 occurs between there. So let's go ahead and find the slope between 4 and 7. We have 150 minus 126 over 7 minus 4, which is 24 over 3 equals 8 people per hour. Okay? Because you were given people, you were finding the people over the hour. So it was people per hour. You've just basically found the velocity-ish. All right, part B. Part B is where I didn't read, so let's make sure we read. Use a trapezoidal sum with 3 subintervals. All fine, I did that. To estimate the average number of people waiting in line during the first 4 hours, I did all 9. Make sure you're reading. So we only care about the first 4 hours that the tickets were on sale. So we're going to have, for part B, we're going to have from 0 to 1, from 1 to 3, and from 3 to 4. We're stopping there, okay? Now, what's our change of x right here? That's going to be 1, that's going to be 2, and that's going to be 1, which means we cannot use the formula for trapezoidal, which means we have to do the right plus the left, and we have to divide by 2. Okay? So I went ahead and I started with the right Riemann sum. Right Riemann sum. What I have to do is I have to take the y value of the 1, and that's 156, and multiply it by 1. Then I have to multiply the y value of the 3 and multiply that by 2. And then I have to do the y value of 4 and multiply that by 1. I ended up with 634. Then I did the left. And the left, so I had 1 times the y value at 0, plus 2 times the y value at 1, plus 1 times the y value at 3, and I ended up with 608. So I did my average, divide by 2, and I ended up with 621 people. But that's over 4 hours, okay? And they said they wanted the average number of people. Okay, well, if that happened over 4 hours, 621 divided by 4 is equal to 155.25 people per the hour, okay? So this right here is the average. Now, if I were doing this, well, first of all, I would have gotten it all wrong because I went all the way to 9. They would have given me point for doing the trapezoidal rule. Yay. Make sure you're reading. So if you're going from 0 to 4 and you find 621 people, yay, you're doing trapezoidal and you did it correct. So you're going to go ahead and you're going to get probably 2 or 3 points. Then if you forgot to get per hour the average, because remember, average, you're doing 1/4 the integration from 0 to 4 of whatever this function is, L of t. So you can't forget that 1/4 when they said average value. So that would probably just be the last point. Okay? But now that we've seen it, you know to look for it. All right, part C. Part C says, for 0 to 9, what's the fewest number of times at which L prime of t can equal 0? Give a reason for your answer. All right, well, to be honest, I kind of graphed this thing. Not like seriously graphed it, I just sort of kind of graphed it. So I had, at 0 it was 120, and then at 1 we went up to 156, then at 3 we went up to 176, but then at 4 we were down here at 126, but then at 7 we were up at 150, 8 we were down at 80, and 9 we were down at 0. So I kind of just did this graph right here. And when would the derivative equal 0? Well, 1, 2, 3 times. Now, they would give you a point for the 3 times. Because good job, that's the right answer. The problem is that you didn't actually say why. So you got to be able to articulate why. Well, think about the definition of a relative max or a relative min. In order to be a relative max or a relative min, your derivative has to change signs, right? So your derivative is positive, and then your derivative is negative, then your derivative is positive, then your derivative is negative. So you're changing directions 3 times. So if you just wrote that, L prime of t, the derivative, if this was L of t, the derivative is greater than 0, or you could say increasing, or you could say positive, from 0, t equals 0 to 3. Then L prime of t is less than 0, from t is equal to 3 2t equals 4. Then it increases, then it decreases. Okay? Now, you gotta say why. Well, you could say the intermediate value theorem, okay? Because if you're thinking about it, if you have gone up and then you've gone down, you have to reach a value at some point in there. I kind of like the mean value theorem better. The mean value theorem, remember, says that the slope of the secant line has to equal the slope of the tangent line. So at some point, it's even kind of Rolle's theorem. So if you wanted to say Rolle's theorem, that would even work. Because at some point, these two things had to be equal, which means you had to have a slope that equaled that as well. So throw a theorem in there. Mean value theorem, Rolle's theorem. The paper also talked about intermediate value theorem. But you got to make sure that you're explaining why. Okay, think about the reason why. You were increasing then decreasing. And what was? You know, the derivative was. It was positive, it was negative. You could say the slope of the function was increasing and decreasing, but yeah, you want to have that slope because they wanted to know the derivative must equal 0. All right, part D, last part. Oh, too bad I have to use the whole sheet of paper for it. Maybe I won't because I already wrote it down. The rate at which the tickets were sold from 0 to 9 is modeled by this ugly function in tickets per hour. Based on the model, how many tickets were sold by 3 p.m. when t is equal to 3? Now, this is tickets per hour, and they want to know how many tickets. That means they're going to integrate, okay? So to integrate, they're just integrating, see, I already wrote it down right here. From 0 to 3, your rate at t. Now, I just put that in my calculator. The rate was that ugly equation, 550 t e to the negative t over 2 from 0 to 3, and I got 972.784, and it tells you to round to the nearest whole number, which is 973. All right, this was a long video, but I hope it helped you out.